Math 1332, Chapter 3, Symbolic Logic, Section 5, Euler Circles, Video 1, Types of Statements Illustrated by Euler Circles. In the previous section, we developed a technique for determining if a logical argument was valid, specifically for a given set of premises, and we called those premises P1, P2, P3, however many of them we had. And some conclusions C. The argument was valid if the following implication is a tautology. The conjunction of the premises implies the conclusion. In other words, the argument was valid if the conclusion logically followed under the assumption that all the premises were true. Recall that in a logical argument, we weren't debating whether or not the individual statements were true or false. We were simply trying to answer the question, if the premises were true, would the conclusion follow? However, there was an underlying property of all statements involved that went unnoticed. In the previous arguments, the ones from section 4, every single statement was unquantified. That thing popping in the background behind me, I'm going to take care of that. All right, that's better. But as I was saying, in the arguments we've seen before, there was an underlying property of all statements involved that went unnoticed. In the previous arguments, every single statement was unquantified. In other words, none of the statements were quantified. And you'll recall that when we talked about statements in a previous series of videos, we talked about statements that were universally quantified and statements that were existentially quantified. The reason we didn't discuss them in the previous arguments is because the approach to analyzing an argument involving quantified statements is different than the approach to analyzing arguments with unquantified statements. Examples of quantified statements are things like, all eagles have wings, with the quantifier being the word all. Quantifies the number of subject that has that property. Or something like, no dogs have wings. In this case, the quantifier is the word no, stating how many dogs have wings. Or something like, some birds are yellow, in which case the quantifier is the word some, because it indicates the number of birds that are yellow, or a general number, not a specific number. Or something like, some birds are not yellow, which is also quantified with the word some. As such, we haven't really analyzed how to determine the validity of an argument like this. Premise 1, all squares are rectangles. Don't look at all that. All squares are rectangles, which is true, by the way, by the definition of square and the definition of rectangle. Premise 2, some squares have a perimeter that equals their area. For example, if a square is 4 by 4, then its perimeter is 4 plus 4 plus 4 plus 4, which is 16, but its area is 4 times 4, which is 16 also. Conclusion, some rectangles have a perimeter that equals their area. Because we didn't make truth tables for quantified statements, we can't use the techniques that we used previously to determine the validity of this argument. So what do we do? In this section, we will learn how to determine the validity of arguments involving quantified statements using a technique called Euler Circles. And as I mentioned in the following comment, the name Euler is pronounced like the word Euler, like the former NFL team, the Houston Oilers. And I believe there's a hockey team whose name is the Oilers, the Edmonton Oilers. I'm not sure, I don't follow hockey. Euler circles look a lot like Venn diagrams and give a visual approach to determining an argument's validity. So the good news is we won't have to set up any truth tables. We won't have to recognize the form of an argument as either being something like the law of contraposition or a fallacy like the fallacy of the converse. Instead, we're going to use pictures. Before we do that, though, let's categorize the types of quantified statements we'll encounter, as each type of quantified statement invokes a different visual. The first type of quantified statement we saw earlier in this video was all eagles have wings. A statement like all eagles have wings is called a universal affirmative. Think about those two words, universal affirmative. It states that all of an object have a property or characteristic. All eagles have wings. By contrast, consider the statement, no dogs have wings. What do you think that would be called? Do you think it would be universal? Do you think it would be affirmative? This type of statement is called a universal negative. Universal for the same reason, negative because we're talking about not having a property or characteristic. It states that all of an object do not have a property or characteristic, all making it universal, not having the characteristic making it negative. The next type of quantified statement we're going to run across is something like some birds are yellow. Now, do you think this is universal? Do you think it's affirmative or negative? Well, it's stating the having a characteristic, so it should be an affirmative, but I wouldn't call it universal. Otherwise, it would say all birds are yellow. This type of statement is called a particular affirmative. So in this context, particular is kind of the opposite of universal. It states that at least one of an object has a property or characteristic. So it's kind of like an existential quantifier. It states the existence of an object as opposed to saying every object has a characteristic. And the last type of statement we'll run across is called, well, let's take a look at it. Some birds are not yellow. What do you think this would be called? At this point, you should be able to put two and two together. It's not universal because it's not talking about all, it's talking about some. So we expect it to be called particular, but it's about some not having a property or characteristic. So it shouldn't surprise you that this type of statement is called a particular negative because it states that at least one, that's the particular, of an object does not have, that's the negative, a property or characteristic. And of course that should say or, both here and here. Can't let that slide. All right, so let's just summarize these four types of statements that we're going to draw Euler circles for. I put them in a nice little table. Universal, particular column, affirmative, and negative rows. So what makes a universal universal? Universal is when you're referring to all of something, which is kind of equivalent to saying none, because when you say none do, you're saying all don't. Whereas particular is not talking about all, but talking about at least one, or saying the word some. And what makes an affirmative affirmative? Well, that means you have something. You have. And what makes a negative negative? You do not have. I didn't highlight the word have here because it doesn't have not. That's kind of implied by the none. So if you just remember that universal means all and particular means some, affirmative means you do have it, and negative means you don't, then it's really easy to remember what these types of statements are.